a lemma. If the set C and D forms a separation of X, and if Y is a connected subset of X, then Y is entirely lie within either C or D. Proof is, here X is equal to C union D and C comma D are both open sets in X, then Y is equal to Y intersection X and putting the value of capital X. So Y intersection C union D, then by distribution property of sets Y intersection C union Y intersection D, the set Y intersection C and Y intersection D both are open in Y with respect to subspace topology. So Y can be expressed as disjoint union of two open sets. If both of them are empty, then Y is disjoint. So it is given that Y is a connected set, so that implies must be one of them is phi. If Y intersection C is equal to phi, so Y is entirely lies in D, and if Y intersection D is equal to phi, then Y is entirely lies within C. Hence Y must be entirely lies in C or D. Next example is 1. So that the set GLNR, that is the general linear non-singular n cross m real matrix, is not connected. Number 2, ONR, that is set of all orthogonal matrix of order n, is also not connected. And finally number 3, so that S to the power n or Sn, the unit sphere in R to the power n plus 1 is connected. Solution is, for first one, let us consider a continuous mapping F GLNR to R such that Fa is equal to determinant A, and obviously determinant A not equal to 0, because GNR contain all such A or all such matrix such that whose determinant not equal to 0 for all A belongs to GLNR. Then it is obvious that F is a continuous function because determinant is a continuous function, and GNR can be expressed as disjoint union to non-empty open set such that GLNR is equal to F inverse R plus union F inverse R minus. R plus is a open set in R and F is a continuous mapping. So F inverse R plus is also continuous, also open set. R plus is a open set in R and F is a continuous mapping. So F inverse R plus is a open set in GNR. Again R minus is also open set in R with respect to subspace topology or usual topology. Then F inverse R minus is also open in GNR because F is a continuous mapping. So GNR can be expressed as disjoint union of two non-empty open set. Why it is non-empty? Because it is obvious. If we consider two matrix, just elementary two matrix, so one of the determinant negative and another is positive. So GNR can be expressed as disjoint union of two non-empty open set. This implies GNR is not connected. For second one, let us choose a mapping G ONR to plus minus 1 such that GA is equal to determinant A. That determinant A is equal to plus minus 1. Why it is plus minus 1? Because A is a orthogonal matrix. So determinant of the orthogonal matrix, it is equal to always plus minus 1 provided all the entry are real number. Here given that all the entry of real number, so determinant of A is obviously is plus minus 1. It is obvious that G is a continuous since determinant is a continuous function, and ONR can be expressed as G inverse minus 1 union G inverse 1. Minus 1 and 1, both of them are open sets in plus minus 1 with respect to subspace topology. So its inverse image under G in ONR is also open. So ONR can be expressed as disjoint union of two non-empty open sets like G inverse minus 1 union G inverse 1. That implies ONR is not connected. And finally, let us consider a continuous function h r to the power n plus 1 minus singleton 0 to Sn such that hx is equal to x by norm of x for all x belongs to Rn plus 1 minus 0. It is obvious that h is onto continuous function, and Rn plus 1 minus 0 is a connected set, then by the above theorem, continuous image of the connected set is connected, so we get Sn is a connected set. Give an example of a finite set which is connected. And next one, give an example of a countable set which is also connected. Solution is, for first one, let capital X be a finite set and tau be a indiscrete topology on X. That is, tau is equal to phi comma X. Then it is obvious that only both open and closed sets are phi and X. So by definition of connectedness, we get X is connected. For second one, let n, that is settable natural number, and tau be the cofinite topology on n to show that n comma tau is a connected set. If possible, let it is not connected. So there exist two disjoint non-empty open sets U and V such that n is equal to U union V. Since U comma V belongs to tau, that means its complements, that is n minus U and n minus V, both are finite set because tau is a cofinite topology, and we know that n minus U is equal to V and n minus V is equal to U. So U and V both are finite set. That implies natural number is a union of two finite set. That implies n is a finite set, which is a contradiction, hence the result. Now we introduce another example, and it is a very important example. The example is the Sorgenfrey line is disconnected, or similarly or equivalently we say, is the space RL, that is R with lower limit topology, is connected. Solution is, here R can be expressed as two part. First of all, minus infinity comma 0 union close 0 to infinity, to show that both sets, first one minus infinity to 0 open and close 0 to infinity, are open sets in RL. Let X belongs to the first set, that means open minus infinity to open 0. Then X belongs to closed X comma 0 open, that is subset of open minus infinity comma 0. Because X is an arbitrary point of the interval minus infinity to 0, so minus infinity comma 0 is an open set of RL. Similarly, if we choose Y belongs to another part of the set, that means closed 0 open infinity, then Y belongs to closed Y comma Y plus 1 open, and that is subset of closed 0 comma infinity. Here Y is an arbitrary element of the set closed 0 to infinity, so closed 0 comma infinity is an open set of RL. Hence RL is a disconnected set. Next theorem is, let XD be a connected metric space. Assume that X has at least 2 points. Then cardinality of X is greater than or equal to cardinality of R. That means if a metric space is connected and contains at least 2 elements, then that cardinality always greater than or equal to the settable real number. Proof is, if possible, let cardinality of X strictly less than R. Since cardinality of X is greater than or equal to 2, so there exist 2 elements A and B belongs to X such that A not equal to B. We define a mapping f X to R such that Fx is equal to D, that is a metric D x comma A for all X belongs to capital X. Now to prove that f is a continuous function, let epsilon greater than 0 and C belongs to real number, C belongs to capital X. Then mod of fx minus fc, that is nothing but mod of d of x comma a minus d of c comma a, and that is less or equal to d of xc, because by using the triangular inequality of a metric, and this is strictly less than epsilon for all d x comma c less than delta, and choose delta is equal to epsilon. that implies F is a continuous mapping. And f of a, just putting x replaced by a, so f of a is equal to d of a, that means 0, and f of b is equal to dba or dab, and that is strictly greater than 0 since a not equal to b. Now to show that closed interval 0 comma dab, and it is equal to closed interval fa comma fb, that is a subset of fx. If possible, let the closed interval fa comma fb is not a subset of fx, so there exists R belongs to the open interval fa comma fb, since fa and fb belongs to capital Fx, such that small fx is equal to d of xa not equal to R for all x belongs to capital X. Then capital X can be expressed as two part. One part is f inverse minus infinity comma R open set, and another part is f inverse R to infinity. Both of them are open and disjoint non-empty open set. Both of them open. Why it is open? Since fa belongs to minus infinity to R and f of b belongs to R comma infinity. So both of them are non-empty, and we know that both of them are open. Why it is open? Because f is a continuous mapping and minus infinity to R is a open set in R. So inverse image of the open set under the continuous mapping is open. So f inverse minus infinity comma R is open, and also similar logic f inverse R comma infinity is also open set, and X can be expressed as disjoint union of two non-empty open sets, that implies X is not connected, that is X is a disconnected set, which is a contradiction, so hence the result. Now we introduce a definition of component. Definition is a connected set C of x tau is said to be a component of X if it is a maximum connected subset, that is C is not properly contained in any other connected set of X. For example, in a connected space X, X is itself a component. That means if a set is connected, then number of component of X is 1. And next theorem is each component of X is closed. Proof is, let C is a component of X without being closed, and C bar is thus strictly larger than C. Then C is a proper subset of C bar, and C bar is a connected subset of X. Since C is connected, so C bar is connected, and this is a contradiction since C is a component, hence the result. For example, let x tau be a topological space and capital X is equal to A, B, C, D, E, that means contains 5 elements, and tau is equal to phi comma x comma singleton A, doubleton C, D, and A, C, D, and finally B, C, D, E. Find all components in X. Solution is, here X is not a connected since X can be expressed as disjoint union of two non-empty open sets. One is singleton X and another is the set B, C, D, E is a disconnection of X, so X is not connected. Again, the set ACD is also disconnected because it can be expressed as two part. One part is singleton A, another part is the set CD. So is also a disconnected set. So the components are singleton A and the set B, C, D, E. Those two sets are the component of X. ACD contains A, but ACD is a disconnected set. That's why singleton A is a component of capital X. Next example is, consider the subspace Q of all rational in the real number space R with the subspace topology. Here each component in Q is a singleton and this is not a open set in Q. Now we introduce the definition of a locally connected space. A topological space x tau is said to be locally connected at X if every neighborhood U of X there exists a connected neighborhood V of X such that V is a subset of U. A space X is locally connected if it is locally connected at each point of X. For example, we choose a set capital X is equal to open interval 0, 1 union 2, 3 be taken as topological space with usual topology, and then X is locally connected but not connected. Solution is X is obviously disconnected, because from the construction of X, X can be expressed as disjoint union of two open set 0, 1 and 2, 3 are two disjoint union of open set of X. So X is a disconnected set. Next, let X belongs to open interval 0, 1 and 0, 1 is a connected neighborhood of X. Similarly, X belongs to 2, 3. Also 2, 3 is a connected neighborhood of X. That implies X is locally connected.